Hello friends, welcome you all to the 25th lecture on function analysis and its application. In this lecture, we will discuss the dual space of C0 is L1. Content of this lecture is the conjugate space or dual space of C0 is L1. Theorem. The conjugate space of C0 is L1, that is C0 star equal to L1. What is C0? C0 is the vector space of all null sequences. The norm of the space C0 is identical to the norm of infinity. Okay, if x belonging to C0, then norm defined norm of x under infinity norm. C0 is the space of all sequences that converge to 0. Proof. Let x equal to infinite dimensional x1, x2 and so on xn and so on belonging to C0, so that C0 equal to x belonging to C0. Then xn is the sequence of x, that is xn converges to 0 as n tends to infinity. If we consider the standard basis En, we can write any sequence x1, x2 and so on xn, 0, 0 and so on in the form of summation k is equal to 1 to n xk ek, and x minus summation k is equal to 1 to n xk ek equal to 0, 0 up to n times 0 and xn plus 1, xn plus 2 and so on. Okay, as earlier already we have discussed how to get this one. Okay, because here x is x1, x2 and so on xn, xn plus 1, xn plus 2 and so on, and here this one in the form of summation k is equal to 1 to n xk ek. So x minus summation k is equal to 1 to n xk ek, that is this minus this. So we have infinite dimensional this one 0, 0 up to n term 0 and then xn plus 1, xn plus 2 and so on. Okay, the norm of x minus summation k is equal to 1 to n xk ek. Here this vector defined the tuples, this one, so this belonging to C0, okay, and norm defined as infinity norm, that is for k greater or equal to n plus 1, that is supremum of mod xk. Okay, so norm this equal to supremum of mod xk. The right hand side of equation 1 represents the remainder after n terms of convergent series equation 1. Okay, hence we get supremum of mod xk converges to 0 as n tends to infinity. Okay, so from 1 and 2 we have x is equal to summation k is equal to 1 to infinity xk ek. Why? Because norm this is 0. Here supremum mod xk converges to 0 as n tends to infinity. It means norm this equal to 0. We know that norm x equal to 0 if and only if x is equal to 0. Applying this property, norm x equal to 0 if and only if x is equal to 0. Okay, applying this property, that is this quantity equal to 0, that is x is equal to summation k is equal to 1 to infinity xk ek. Equation 3. Let f belonging to C0 star and let Sn equal to summation k is equal to 1 to n xk ek. Then equation 3 shows that Sn converges to x as n tend to infinity. Okay. Since f is linear, then f of Sn equal to summation k is equal to 1 to n f of xk ek. Okay. So f of Sn equal to summation k is equal to 1 to n xk f of ek. Since f is continuous and Sn converges to x as n tend to infinity, as here, we have f of Sn converges to f of x as n tend to infinity. Okay, because f is continuous, which gives fx equal to k is equal to 1 to infinity xk f of ek. Okay, equation 4. Hence, equation 4 gives the form of continuous linear functional on C0. Let us take f of ek is equal to alpha k and show that the mapping T such that C0 star to L1 given by Tf equal to alpha 1, alpha 2 and so on alpha n dot dot dot, where alpha k is f of ek. That is, this is equation 5. Is an isometric isomorphism of C0 to L1. First, we show that the mapping T defined above C0 star to L1 is well defined. To prove this, let us take x belonging to C0, where x is equal to beta 1, beta 2 and so on, beta n, 0, 0 and so on. So that f of x equal to summation k is equal to 1 to n alpha k beta k. Okay. Since x is equal to summation k is equal to 1 to n beta k ek. Okay. So fx is equal to summation beta k f of ek, and f of ek is alpha k. Okay. So this is valid. Fx is equal to summation k is equal to 1 to n alpha k beta k, where beta k is equal to signum alpha k bar for k lies between 1 to n, and for k greater or equal to n plus 1, 0. Now, norm of x equal to supremum of mod beta k. Okay, because x belonging to C0. So, norm x defined supremum of mod beta k, and beta k is signum alpha k bar, that is supremum of mod signum alpha k bar, and we know that by the property of signum function, mod of signum alpha k bar is 1. So, norm of x is equal to 1 here. Further, alpha k beta k, when k lies between 1 to n, alpha k signum alpha k bar, okay, that is mod of alpha k, okay, by the property of signum function, which has been already discussed. Hence, summation k is equal to 1 to n mod alpha k. Okay, here mod alpha k. So we can write this is summation of this, that is summation of alpha k beta k. So this is mod alpha k, that is positive term. Here summation alpha k beta k is fx. So here summation k is equal to 1 to n mod alpha k can be written as summation mod of alpha k, that is mod of summation k is equal to 1 to n alpha k beta k. We can write, okay, because this is the positive term. So this can be written as mod of fx. Okay, mod of this, that is mod of fx. And f is linear functional. So mod of fx less or equal to norm f into norm x. Okay, and here norm x is equal to 1. So that mod fx less or equal to norm f. Okay, that is summation k is equal to 1 to n mod alpha k less or equal to norm f. Since k is equal to 1 to n, mod alpha k is bounded here. Monotonic increasing sequence, it is a convergent sequence. Hence we get summation k is equal to 1 to infinity mod alpha k less or equal to norm f, which implies that alpha n belonging to L1. So alpha n, which is the image of f under T, belongs to L1, so that T is well defined. Next we show that T is onto L1. Taking beta k belonging to L1, we have to prove that there is a G belonging to C0 star such that T maps G onto Bk. If x belonging to C0, let us write x equal to summation k is equal to 1 to infinity xk ek. As usual, we can write. We can take required G as gx equal to summation k is equal to 1 to infinity xk g of ek. G of ek, that is beta k. Okay. Since the representation of x is unique, g is well defined, and further it is linear on C0, to show that g is bounded, consider taking modulus of both sides. So mod gx is equal to modulus of k is equal to 1 to infinity xk beta k. This is less or equal to summation k is equal to 1 to infinity mod of xk beta k. But summation k is equal to 1 to infinity mod xk beta k less or equal to supremum of mod xk summation k is equal to 1 to infinity beta k. Okay, if you expanding this one, mod xk beta k under the summation k is equal to 1 to infinity, so it can be written as x1 beta 1 plus x2 beta 2 plus and so on, xn beta n and so on. So taking each xk is maximum in each term. So we can take the supremum of mod xk common. Okay. So supremum of mod xk into summation k is equal to 1 to infinity beta k, we can write this less or equal to this one. Therefore mod gx, value of this is less or equal to this, that is mod of gx less or equal to norm x into summation k is equal to 1 to infinity beta k. Okay, this shows that g is well defined, linear and bounded on C0. Okay, therefore g belonging to C0 star. Since ek belonging to C0 for all k is equal to 1 to 3 and so on, that is k belonging to natural number, we can take g of ek is equal to beta k for any k. so that Tg equal to beta k. Okay, that is infinite dimensional beta 1, beta 2 and so on, beta and 0, 0, 0 and so on. And T maps C0 star onto L1. We show that norm of Tf is equal to norm of F, so that T is an isometry. Since Tf belonging to L1, here F is the element of C0 star, that is Tf is the element of L1. We get summation k is equal to 1 to infinity mod alpha k equal to norm of Tf, because here Tf is infinite dimension of alpha 1, alpha 2 and so on. Okay, so if f belonging to L1, then norm of Tf equal to summation k is equal to 1 to infinity mod of alpha k. Okay, so here we have this, and using equation 6, mod alpha k less or equal to norm of f. Okay, so this quantity less or equal to norm of f. Equation 7. To prove the reverse inequality, okay, we have proved here norm of Tf less or equal to norm of f. Now we have to prove norm of f less or equal to norm of Tf. To prove the reverse inequality, we get x belonging to C0, so that x can be written as summation k is equal to 1 to infinity xk ek. Hence, f of x equal to summation k is equal to 1 to infinity xk f of ek. F of ek is alpha k, as in equation 4. So, mod of fx equal to mod of summation k is equal to 1 to infinity xk alpha k. Okay, and this can be written as less or equal to supremum of mod xk and summation alpha k. Okay, because if we take supremum value of xk in the expansion of this summation, okay, so we can take supremum of mod xk out of this summation. Mod f of x less or equal to supremum of mod xk into summation k is equal to 1 to infinity mod alpha k. We can rewrite the last inequality as this is mod of fx and less or equal to this is the norm of x, okay, because x belonging to C0. So mod of fx less or equal to summation k is equal to 1 to infinity mod of alpha k norm x. So dividing norm x both sides, which implies that supremum x not equal to 0 mod fx upon norm x less or equal to summation k is equal to 1 to infinity mod of alpha k. Okay, and summation k is equal to 1 to infinity mod alpha k is norm Tf using equation 7. Okay. So, supremum of mod fx upon norm x, that is norm of f, using the definition of norm of f, that is this one is norm of f, less or equal to norm of Tf, equation 8. Now from equation 7 and 8, we get norm of Tf is equal to norm of f. Okay. In 7, norm of Tf less or equal to norm of f, and in equation 8, norm of f less or equal to norm of Tf. It means from 7 and 8, we get norm of Tf is equal to norm of f. From the above definition of T given in equation 5, okay, this, we see that it is linear. Since it is an isometry. It is 1 to 1. We have already proved that it is onto. So that T is an isometric isomorphism of C0 star onto L1. In other words, C0 star is equal to L1, which completes the proof of the theorem. In this lecture, we have discussed the conjugate space, that is dual space of C0 is L1. That is C0 star is equal to L1. These are the references which have been used in this lecture. Function analysis, Dover publication written by George Beckman and Lawrence Naresy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.B. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.